Hello everyone, how are you? Fine. Today we are going to discuss time-dependent perturbation theory. Time-dependent perturbation theory is a very important theory in quantum mechanics. Before coming to the time-dependent perturbation theory, let us discuss some other important part which is connected to time-dependent perturbation theory. In this one, we are going to see Dirac notations. Dirac notations are very important to understand time-dependent perturbation theory. And here we are going to see Dirac's Bray and Ket notations because it is from the bracket one. So bracket is split into two parts. One is Bray, another is Ket, and that is why it is known as a Bray and Ket notations. The values of Schrodinger wave equation phi r at various points r are equivalent to component of vector v. Dirac used ket phi symbol pronounced as ket phi for the state phi of the dynamical system and considered as a counterpart of vector v for a vector in a three-dimensional space. Corresponding to every vector ket phi, there is a conjugate vector Bray phi, known as a Bray or Bray phi. In the matrix notation, ket phi is represented as a column matrix. So here ket phi represented as a column matrix, phi 1, phi 2, up to phi n, different components. And Bray phi is represented as a row matrix or a transpose complex conjugate. So Bray phi is represented as a row matrix and a transposed complex conjugate means phi 1 star, phi 2 star, a complex conjugate. The scalar product is represented as phi 1 star, phi 1 plus phi 2 star, phi 2 plus the other terms. The equivalence between Dirac notation and Schrodinger notation is given as Bray and Ket phi integration phi star r, phi r dr. Now we come to the another slide. In this one, we are going to see how the time-dependent perturbation is formed. The time-dependent perturbation, the time-dependent part of Hamiltonian can be regarded as a perturbation and can be solved by means of perturbation theory. This is called time-dependent perturbation theory. The Hamiltonian can be of form H1. Hamiltonian can be of form. There are two, one H1 and another is H0. So H is a function of time, H0 plus H1t, and that is known as equation number 1. H0 is unperturbed time-independent Hamiltonian. So in this term, H0 is time-independent or unperturbed Hamiltonian. And it is solvable in terms of stationary states H1 in the time. And the perturbation is a very small perturbation over H0. So it is having a two different terms. H0 is a time independent one and it is unperturbed. H1 is the time dependent one and it is a perturbation. And it is an admixture between the two. And it is forming a total Hamiltonian, which is time-dependent one. So time-dependent interaction causes admixture of the eigenstates of stationary Hamiltonian H0 and the Hamiltonian H1. Now, general formulation for obtaining a perturbation solution of Hamiltonian of equation 1. One can expand eigenstates ket psi t of the following form, and it is in terms of a full Hamiltonian in terms of stationary eigenstates ket phi n. So ket phi n is the stationary eigenstate which does not change with time, and that is of the time independent Hamiltonian H0. So we try to see that how the time independent Hamiltonian is useful. Now ket psi t is equal to summation over C and T ket phi n. Ket phi n is the stationary state. It is not dependent on time. This is a coefficient that is depending on time because C and T is a function of time. And if H 1 is 0, then Cn0 exponential minus I et divided by h cut, and that is equation 3, which is a coefficient which is time dependent. Using Schrodinger equation, H0 cat phi n En cat phi n. So these are the eigenstates. It is the Hamiltonian operator eigenvalue. Here En is the energy of the stationary state cat phi n. Now therefore redefining C and T using equation 3 and equation 2. This is equation 3 and this is equation 2. We can write cat psi t equal to summation over n C and T exponential. Here it should be minus I E N T divided by h cut cat phi n. Now using equation number 5 in the modified Schrodinger equation of equation number 1 and in equation number 4. So we are using two different equations. That is the equation 1, and also we are using the Schrodinger equation and using this particular modified form. So if we take this is the time dependent part, and we are taking a derivative with time. So first this will be differentiated, and in second one this will be differentiated. So here I h cut dc and t by dt. So we are differentiating this. The exponential term is as it is. And in the second term, I h cut c and t is as it is. The differentiation is taken for the exponential term. So it is minus I e n divided by h cut and the exponential term as it is, cat phi t, and equal to summation over n h0 plus h1 C n t and e to the power minus I e n t divided by h cut and phi cat phi n. Now we try to replace this h0 with en. So h0 cat phi n equal to en cat phi n. So we can replace this h0 by en. So that we'll see in our next slide. So rearranging the equation 6 and using the energy eigenvalue En for time independent part of Hamiltonian. So again, we are taking the exponential term out of the bracket, and again we are taking the exponential term out of the bracket, and we are replacing h0 by En as we have mentioned in our previous slide. Now we'll notice that here CNT En, if you open the bracket again, CNT En. So both the sides CNT En, here also CNT En, so it cancels out. So remaining term is IH cut dCNT by dt, exponential term cat phi nt, again summation h1t cnt e to the power minus IENT divided by h cut cat phi n. This is equation number n. Now we are taking the scalar product Bray phi m from the left hand side and using the orthogonality condition that bracket phi m phi n equal to delta mn. And we know the condition, orthogonality condition, that m is equal to n, then delta phi n, delta mn becomes 1. And if m is not equal to n, this becomes 0. So this orthogonality condition is imposed for a special purpose, to have a distinction between the two different states. And for obtaining distinction between two different states, we'll try to use the orthogonality condition. In our day-to-day life, if we want to perform some work, then we ask that who will be helpful to us. So in general, out of the few people, some people will be helpful to us, some people will deny to help. So people who are denying help, their m is not equal to n, 0 means they are not helpful. And people who are we are ready to help, then m is equal to n, and we have a delta mn 1. So there are two different conditions, that one helpful, another not helpful. So to impose the two distinction between the two different states, we are using the orthogonality condition. And in that case, we try to name this CNT as CMT, and CN and EN is termed as EM. And here we have done that particular modification, that dCm instead of dCn. And here e to the power minus IEN, here e to the power minus IEM rather than En. And we have taken a scalar product from the left hand side with m. Again, scalar product from left hand side m. So here we'll see that we try to modify this equation that IH cut dCm by dt exponential term phi m. So both phi m. So bracket phi m delta mn is equal to 1. And again, we have on the right hand side bre phi m h1t cat phi n cn t e to the power minus I e n t divided by h cut. Now we make all this term on the one side. So that we are going to see on the next slide. So rearranging the equation, IH cut dCm t by dt equal to summation over n bre phi n h1t cat phi n and cnt e to the power I em minus ent divided by h cut. That is equation number 9. Now we come to the first order theory. One can expand Cn as a perturbation series. We have seen in the time independent perturbation theory can be expanded into perturbation series. Similarly here, it can be expanded into perturbation series. Cn equal to Cn0 plus Cn1, Cn2. That shows different type of orders. Suppose initially the system is in the particular eigenstate phi I, that is the initial state of H0, that is the time independent perturbation. So it can be represented Cn0. It can be considered as Cn state 0 or first order, and it can be considered delta Ni. Ni means initial one. Now using equation number 9, 10 and 11, we can write IH cut dCm1, which is a first order t dt, and summation over n bre phi n h1t cat phi n e to the power I em minus ent divided by h cut. And this is the differentiation form. To solve it, we have to integrate it. So dCm1t, and the rest of the thing goes on the right hand side. So minus I divided by h cut 0 to t dt prime e to the power minus e to the power minus m t prime divided by h cut bre phi m h1t prime and cat phi I. Now it is the initial condition. And we have used the dummy variable, which are shown by prime. Now dummy variable is a special type of variable to have a distinction. Then when we put the integration limit 0 to t, the dummy variable loses its identity and becomes t. Now when it is not integrated, it is in form of a dummy variable shown in terms of prime. But when we put the limit, then it loses its identity and it becomes normal variable t. So it is known as a dummy variable because of this particular reason. Now including the first order, C1mt is equal to delta mi. I is the initial condition minus I divided by h cut 0 to t dt prime e to the power I em minus ei t prime divided by h cut and bre phi m h1 t prime and cat phi I. That is equation 13. Now this solution is reliable if it follows that modulus CMT is very, very less than 1. So according to the measurement postulates, the probability that the measurement of H0, that is the time independent Hamiltonian of the system at time t, will be given, in the form of E1 is I to m is equal to modulus CMT square. Now this is showing a probability of transition from I to m. So this equation can be represented in words. This is the probability that the system has made a transition or a quantum jump from I to m. The probability that the system starts in the system cat phi I, that is the initial system, and ends in the state bre phi cat phi m at time t is given by modulus square of expansion coefficient CMT. So initial state is cat phi I, final state is cat phi m. And at time t, the transition is taking place, and probability of transition is represented by this particular form. It is the expansion coefficient modulus square. So this is the important result of the time-dependent perturbation theory. Now we come to the importance of time-dependent perturbation theory. This theory is useful in laser physics, where one is interested in the population of different atomic states in a gas when time-dependent electric field is applied. So in a laser physics, this is very important to apply time-dependent perturbation. And these probabilities are also useful in calculating the quantum broadening of spectral lines and in particle decay in particle physics as well as in nuclear physics. This theory can be used for explaining transition in nuclear magnetic resonance spectroscopy. So this is a very important theory, and in a book written by Amit Goswami, it is mentioned that when atom is taking bath in electromagnetic radiation, time-dependent perturbation is applied. For further reading, I suggest that one can refer Quantum Mechanics by Amit Goswami. And now we come to the slide which gives the information regarding the contributor. The time-dependent perturbation theory was introduced by Dirac, and he also gave the Dirac notations. So Paul Adrien Maurice Dirac, born in 1902, passed away in 1984. He was British physicist and Nobel Prize winner. And the last slide is the Department of Physics in a new look. This is my office and a new look of Department of Physics. So